Today, I'll be walking you through the depth estimation baselines that we have for you. And before we begin, let me talk a little bit about what monocular depth estimation means. It's a pretty interesting problem in deep learning where we have single RGB images, and our job is to predict the depth at which each pixel is from the point of observation. This is slightly different compared to stereo depth estimation, where we have two images for every scene. So taken like you can imagine it like how we perceive depth using two eyes, and we can see the difference, and our brain automatically calculates how far away something is. So it's a relatively simpler problem if you have two images side by side, which is what stereo depth estimation is, but it's significantly harder when you have just a single image and your job is to predict the depth in those scenes. This dataset has been generated synthetically using the Carla simulator, which is used for which is simulator that's used for trying different self-driving techniques and other techniques related to autonomous driving. So the purpose of this notebook will be to get you acquainted with the format of the dataset, which is relatively simple as far as datasets are concerned, and also go about how we can begin thinking about solving the problem. What are the biggest things you need to look out for and stuff like that. And so, yeah, proceeding to setting up our workspace. So we will be using the AirCrowd CLI, which can help us download the datasets, make submissions, and log in and authenticate ourselves while making those submissions, and provides a bunch of these utilities so we don't have to manually try and download the datasets and stuff like that. So in this case, we will be setting it up for the depth estimation challenge, which is signified by the -c parameter. And we will then be extracting all the data sets to a data directory. So we have it all in a single location. And you can use the file explorer in Google Colab to kind of explore and look at those images yourselves if you would like to. Then we will proceed to import the libraries that we will need to solve the problem for today. Relatively simple. We'll be using a relatively simple approach, so we will not need too many imports. We have some standard utils and some utils for the deep learning side of things, TensorFlow specifically, and some for just normal image manipulation. So setting up the data, first we initially point it to the path to the downloaded locations, which you can find after extracting the data. And we will then construct data frames out of it. So data frames are easier to work with when you want to pass it on to a model. You can pass just the data frames with the paths for the X and Y, X being the RGB images and Y being the depth maps in this case. And that makes it easier to read file locations as opposed to directly reading the file names from the directory. So we construct data frames that look something like this. So we have the path to a particular image, and the corresponding label is essentially the depth map, the path to the NPZ array. I'll get to what that is in a little bit when we get to the cell where we unpack and open and extract the stuff out of the dataset. Taking a look at how big our dataset is, we have 4,800 training images, 1,200 validation images, and 2,000 test images. So the test images do not come with depth maps because that's evaluated using the private depth maps that are hidden in the server. Essentially, when you make submission, those are the depth maps that are used as ground truth. You can use validation images to actually check how your model's performing when you train it, and it can be like this hidden unseen data set. And we ensured our best to make sure that the scenes are not too repetitive, as in at least the starting locations, because there's a limited number of maps available in Carla, and we've ensured that the scenes are not too familiar to at least when you look at them across different data sets, there are going to be a little bit of difference, as in their starting locations could be different, the kind of traffic they encountered could be different. So there is a little bit of difference here. So then we'll proceed to write something called a custom data sequence generator. So what this is it allows us to dynamically load in batches of data and feed it to the model without having to load the entire data set as a whole before we even train. So typically when you train a model, you would have passed in the X and the Y labels as it is, and the model would begin training on that. But if you want to store all the data in variables, you will need to load them into memory. And sometimes when you're dealing with data sets like images and other kind of data that can take up a lot of memory, you pretty soon you're going to run out of memory and you can't train anything. So this solves that problem. What it does is dynamically, as you can get data batch by batch, and you can load that into memory, train on it, take it out of the memory, and then train on the next batch and so on. So it allows us to do exactly that, and most of this logic is implemented by the user, whereas it expects some methods to be defined. So we will need to refer to the base class, which is the sequence base class, and I will first explain what the necessary methods are, which are just these two, underscore underscore len and underscore underscore get item. What they do is len gets called whenever you call the Python's len function on top of an instance of this object. So this is standard for any class. Whenever you override the len method, it will be called whenever you call the len function using standard Python. So len of an array returns the length of the array. In this case, it would return whatever you define the logic here. Similarly, get item is called whenever you index an element out of this object using the square brackets. So if you're taking an element out of an array, it would pass that index to this parameter right here, and whatever logic is over here gets called. The list class in Python takes care of all of this. Here, since we're defining a custom class, we will need to override. The reason for overriding these things is here you're expected to pass it a particular batch ID. So batch IDs are essentially sequential numbers that increment until you run out of batches. And what you're expected to return is an X and a Y. So that's the actual X values and the ground truth. So they can train against and minimize the loss for that. And another case is if you're using the test data set, you don't need to return Y, and we will need to explicitly mention that, since I did mention most of this logic is implemented by the user. And so the purpose for overriding the len is so when you give the data generator to the model to train, it's going to call each batch in like by its index one by one until it runs out of batches, but it'll only know how many batches there are if you give it the len parameters. So they override the len method. So it uses that to determine how many batches there are so that it can exit gracefully. Another method that can be overridden is on epoch end, which essentially, like it says, gets called on the end of an epoch. So in this case, it shuffles the data set, and so the next epoch essentially deals with different batches of data, at least same batches of data, but in different orders. The other methods that we've defined here are load and data generation, and these are just methods that you could call anything and define. These are not required to be overridden by Keras. So in this case, what we're doing is you will need to load in the images themselves. So you will need to load in the actual image and the depth map manually and load it into a variable. And we will need to do that for a batch of images. So the batch size can be anything, let's say 8 images per batch. So you will need to load 8 items one by one and store them as a batch variable. And then the get item returns that. So this is where we have the logic. We usually write a helper method to write the logic for loading in the images and post-processing them, and post-processing the label as well if needed, and passing it on to the model. So in this case, we will be applying a certain augmentation techniques. In this case, we are randomly cropping the center of the image and feeding it to the next step. So why are we random cropping? So the dimensions of these images are they have a height of 300 pixels and a width of 900 pixels. When you're dealing with UNets, you'll notice that it's better to work with square images as often as possible. It's really tricky to work with non-square images, especially because you're downsampling in each step and you're upsampling later on. So because of that, we will be dealing with square images, and we can specify a custom width and height, and it'll crop that region out of it. The important thing here is that by random cropping, you're not focusing on one particular area of all images all the time. You're randomly taking different sections of images for every batch. for every image. So it deals with closer pixels and further away pixels. So it generalizes to larger images as well in the future. And taking a look at the NPZ arrays that I mentioned earlier. So the arrays that are the depth maps are just single channel black and white images, right? So we've saved them as NPZ arrays strictly to save space and make it a small file for people to download. And we will be making a submission as well in the same format. So we want that to be tiny as well. So how NumPy np.savez compressed works is that you have you save an array into a particular file, and you could save multiple. You could save a list of arrays, and each one is stored under the keys arr_0 and 1, 2, 3, and so on. In this case, we have only a single array, so we by default it's stored in the arr_0 key. So we are loading the entire this compressed array, which is essentially a large dictionary with multiple keys, which could have multiple keys, each key corresponding to one array that was saved. And you could additionally override the names of the keys in this case, but we haven't done that. So we're using the default key name, which is arr_0. And that returns the single channel depth map. And since it is an image, it contains pixels in the range of 0 to 255, so we will be normalizing it in the range of 0 to 1 just by dividing it by 255. Finally, we will resize it to the target dimensions in case the crop exceeds the boundaries or something like that. It can stretch, so we will need to resize it just to ensure. So in the case that you're not going to crop, you will need to resize it to a target dimension. And data generation is essentially a wrapper over the previous method that we did. So it calls self.load for every element in the batch and populates an empty array that we have over here that will in the future contain the X and the Y batch itself, which is then in turn called by the actual get item method, which returns the X and Y. Then we'll proceed to just define the hyperparameters that we plan to use for training. In this case, they will also be applied to actually specify the dimensions of the data set and so on. So in this case, we have a height and width of 256, a learning rate of 2e power minus 4, which you can play with. And we'll be training it for 25 epochs and a batch size of 64 images per batch. We've then written a helper method to just visualize one sample of the data, one batch of data. And you can go through what goes on in here. It's essentially using matplotlib to plot the images side by side. So taking a look at what the dataset actually looks like, we'll see that there are randomly cropped RGB images, which are 256 in dimension. And all of these images come from a larger 300 by 900 image. And their corresponding depth maps are essentially pixels in the range of 0 to 1. And so we use the color map to actually visualize how they look, and you'll notice that blue values are lower and they're closer to the point of observation, whereas red values are further away from the point of observation. So it gets red as it goes far away from the point of observation. And one very important thing to note here is some data sets, in some data sets, the values are scaled logarithmically, whereas in some data sets they are not. In this case, it's very important to note that the values are scaled logarithmically. So what this does is it allows for more precision in values near to the camera. It's what we're interested in. The values closer to the camera, or things that are in immediate interest to us, or things that could collide with us, or things closer to us. And things further away are not of immediate interest to us. So when we get closer to them, we can increase the precision for them. So when you logarithmically scale the depth maps, it would lead to a lot of precision in the areas nearby, and precision dies as you get further and further away from the camera. And in most cases, if the data is not scaled logarithmically, you will need to scale it yourself. Now let's talk about actually building the model that we'll be using to try and solve the problem. Since that this is a relatively simple baseline, we will be going with a relatively simple approach and a custom network. But what I want you to think of is what kind of problem is this and how do we begin solving it? Think of a segmentation problem where we have an image and we have different classes in the image that are segmented using a segmentation model. And for example, let's assume that there are 10 classes that every pixel in the image could take. This is pretty simple. We have an image as an input and we have an output, which is an image of the same dimension. And we have classes in the range of 0 to 255 or 0 to 1 after being normalized. So you could argue that in theory, this problem is pretty simple, except it has quite a lot more classes than a segmentation problem. So once you think about it like that, we can begin trying to use a unit to actually solve it. So we'll be building a relatively simple unit architecture. And a unit architecture consists of a downscale blocks and upscale blocks, and in the middle it has a bottleneck layer, which are just dense layers. So it takes an image, it embeds it into certain features, and those certain features go through a few dense layers, and then it begins upscaling those features and reconstructs another image out of it, which is of the same dimension. But what it learns is entirely up to what kind of ground truths we use and what kind of loss functions we use. And you'll notice that most of the emphasis is placed on those sections. So like I mentioned, these networks are relatively simple. Feel free to go through them and change parameters here and there, but none of them should really lead to too much improvement in performance compared to the hyperparameters or tweaking with the loss functions, for example. So taking a look at the loss functions, we have a single utility which takes in a target and a prediction and returns a loss. So there are three kinds of losses which are embedded into this function. So first is the structural similarity. And so we use the structural similarity index metric to actually find how similar another image is to our current image in terms of its structure and the content it represents. And it uses, like we mentioned here, luminance, contrast, and structure to actually compute that similarity. It's really useful to ensure that features don't get degraded and details are captured when in the predicted image. Otherwise, it could just be a blur and a mess. And we also use an L1 loss, which is just a standard loss we use for pixel to pixel a comparison, how far your predicted pixel is from the ground truth, how far away is your prediction. And finally, we have an edge loss, which ensures that we have sharp edges and around features that we expect sharp edges to be, like the corner of a car, for example, or other features like labels and things like that. We expect sharp edges there. So this loss ensures that we get crisp edges without degrading the quality and making it a large, massive, like a blob of color, let's say. And we have assigned weights to each of these losses, and feel free to tweak them, but play around with them and kind of place more emphasis on one loss or the others and stuff like that to ensure that you get the best results. So you are encouraged to highly play around with these values over here. And coming over to the actual model, we constructed using the layers that we mentioned above. So we have downscaling blocks and upscale blocks, and we have a bottleneck layer which goes in the middle. So constructing the model using them, and we also specify the loss function will be the utility that we just mentioned earlier. So finally, getting to training the model itself, we will be using the Adam optimizer with the learning rate that we specified earlier, and we will create an instance of our model so that we can actually call the dot fit, which should be pre-specified by the base classes defined in keras.model. And like I mentioned, you could just pass it a data loader, a custom data sequence generator in this case, and it will take care of finding out how many batches of data there are and indexing each batch out of it and training your model and printing the metrics that you mentioned out to standard out. So after you compile the model with the optimizer that you mentioned, and we've already included the loss function as well, and how we optimize the loss function is hidden inside the model itself. We will then proceed to call the dot fit method using the train loader, for the number of epochs that we specified earlier. And the validation data will take in the validation loader as the value for the parameter. So training it for 25 epochs, and we'll notice that the loss begins to reduce or like gradually. And like I said, you could play around with the hyperparameters, the number of epochs, and the weights for the losses to try and squeeze more performance out of this model. Although you must remember that this is a relatively simple model, so you can't expect the best performance. Then we can actually plot those metrics using the history object that's returned by the dot fit, and it contains all the metrics that were trained for every epoch. So you can use you can take the values out of it and call dot plot, and we'll notice that the loss reduces, and at one point it doesn't reduce too fast, so you could call it a little saturated at this point. And the validation loss has some spikes, and that usually tends to be the case, but you should more or less take a look at the overall trend of the validation curve, the loss curve. If you are satisfied with the model, you could then proceed to feed the test data and then predict the data, the samples on the test data set. Before that, let's take a look at what the model predictions actually look like against some samples in the validation data set. So taking this image and loading it into the data set, this is what the depth map actually looks like, and this is what the model has predicted. So you'll notice that there is a lot of blurriness going on, and it's not the best model out there. But it's important to realize that this is one of the more challenging problems that we have, and a simple model is just not going to cut it to do good in such a problem. Although I would say that it gave a reasonably good performance considering how difficult the problem is. You'll notice that there's a lot of blurriness going on, so you could play around with the edge loss and the structural similarity index and give them more weightage over the pixel-wise loss and try to get better accuracy out of it. We have also written a utility to try and visualize this predicted depth in 3D, because these are pixels that range from 0 to 1 or 0 to 255, which are taking the images. And you'll notice that it's performed as well as it could. And I did mention earlier that the values closer to the camera are more precise than the ones further away, because how we scaled it logarithmically. And you'll notice that that's the case in the ground truth, and the prediction is pretty similar to that in that sense. Like, it looks pretty similar to what the ground truth is in three-dimensional, as taking a look at it in a three-dimensional graph. Then we'll proceed to construct a data loader using the test set, and where the height and width has been changed, so we will have to rescale it to our desired height and width once it's predicted. And so one thing to notice here is that we want to make the submissions in the expected height and width the evaluator expects, right? So that would be the original dimension of the image. So now we have images of 300 to 900. What we can do is resize once the prediction is done. So that way we can preserve the size, and it is going to be interpolated because we will be using cv2.resize to actually resize the predictions. But there are many cases where you cannot fit such large images, at least a large number of such images with a size of 300 by 900 into the model directly. And since we have trained it on a particular size, we're going to have to go with that for the rest of even testing. So the test data set is loaded in with images 256 by 256, and we will not be shuffling because it is the test set. We want to preserve the order in which the images are predicted, and we have the predictions in wipe red. And taking a look at those predictions, we'll notice that there are 2000 images with 256 by 256 as their dimensions, and a single channel. Because there is a single channel in depth map, we will be ignoring this channel. So taking those predictions out of them and resizing it to the size we want, we will then be storing it as an int16, and we will be appending all this to a large array. Finally, we will construct compressed NumPy arrays using the same predicted values, and we will be storing it in the format that I mentioned earlier. So by default, when you load a particular load a particular array into a compressed array, it's going to save under the ARR_0 key, so you don't have to override it over here. So the two parameters that the saveZ compressed method takes is file name and the array itself. So we will be passing in the file name and the predicted array. And it's important to note that the file names are the same as the input file names, which are the same, the images, the index for the images, the image IDs, you could say, and just suffixed with the .npz extension. Finally, we will zip the predictions file into the assets directory, and we will call the notebook submit utility of the AI crowd magic function. Finally, the only thing left to do is make our predictions on the test data set, for which we don't have the ground truth, and submit it to the AI crowd evaluator. So before we begin, we need to understand that the evaluator expects the images to be in the same dimension that were given in the first place, but we train the model on a different size. So we will need to resize the images back to the size the evaluator expects before we can submit it. But we have trained the model on a particular size, 256 by 256 in that case. So we will be first pre-processing the test data set to be of that size. And one thing you'll remember is that the data loader that we wrote earlier should take care of resizing it. And in this case, we're going to predict each image one by one, just to make sure that we don't run out of memory or we don't crash for any unnecessary reason. It can be a little inefficient, but it gets the job done. We won't be shuffling because the order is important, the order in which the images are predicted. And we will pass it on to the model. The data loader can be passed on to the model for predictions. And the predictions are stored in this variable ypred_test. So taking a look at the size of this large array, you'll notice that there are 2000 samples, which correspond to 2000 images that were there in the test set. Each image is a 256 by 256. It has a dimension of 256 by 256, which is the size we trained it on. And there's a single channel, which will be disregarded because we can just collapse that axis. So then we will proceed to resize all these images, as it is important to A, resize them, and B, also convert their scale back to 255, because that was what the original images came in. And once we have it in that format, exactly like that was expected, we have essentially 2000 single channel images of size 309, height of 300 and width of 900, and each pixel value varies in the range of 0 to 255. We will then save it into the compressed npz arrays, like I mentioned earlier. So for that, we'll be making use of the np.saveZ compressed method, which takes in a file name and a prediction. In this case, it's just the array, a file name and the array. The file name will be the same as the file name of the image, except suffixed with the .npz extension. The array, you can just pass it down as the second parameter, is the array that was predicted, which is of the size to 300 by 900, 300 being the height and 900 being the width. And like I mentioned earlier, by default, it stores it under the ARR_0 key. So we don't have to mention that explicitly here. And that will be taken care of the evaluator, which searches for the first ARR_0 key in every saved NPZ array. This would lead to a relatively small file size, which we can zip into a zip file. And finally, we will be making use of the notebook submit flags of the AI crowd CLI magic function and submit it for the depth estimation challenge. And what we're submitting is the assets directory where we stored the zip file of predictions. No, if I would just basically wouldn't check for, wouldn't run the code locally, so you don't have to worry about it crashing in any way, because without that, it would try to run the whole notebook locally to make sure that it runs end to end, which is not important for our purposes. then you can use the following links to take a look at what the submissions look like. And we also have a visualization where we show what the predicted video looks like on the test set. And after that, you can follow these links to uh, explore the documentation for Keras and read about UNets and try and see if you can incorporate other techniques to boost the score here. Although it's important that you realize that this is a pretty hard challenge, and a simple network will only get you so far, even with optimizing it a lot. You can squeeze a little bit of performance out of it, but it's not going to be uh, enough to provide the best scores and give scores way closer to the ground truth than they already are.